So, hello everybody and welcome to my third session on statistical energy analysis and hybrid methods. This time we will extend the harmonic oscillator concept by using multiple masses on much more complex systems of these bulk systems, and you will learn how in principle complex deterministic subsystems are described. So we come, in the first step, we just will use a double degree of freedom system, which is a kind of extension to our harmonic oscillator. So now the arrangement is now in a horizontal way. We have two harmonic oscillators, more or less. This is one, and this is the other one. And those harmonic oscillator, which represent the mass in the spring, they are coupled by an additional coupling spring in the middle between the masses. So as a consequence here in our equation of motion, this looks exactly like the old equation of motion, but it's double because we have two of them. We have an external excitation and we have a coupling term which is depending on the distance between both and has different directions, obviously, which is given by this one. Again, we use the complex mathematics to solve this with, again, our positive J omega convention, and we can write, so we get rid of all the derivatives. Normally, such things are written in matrix form, and if we are neglecting the time dependence as usual, we can write the matrix form like this. So we have the global matrix giving the dynamics of those 2 degrees of freedom, which are the 2 displacements, and those are the external excitations or exciting forces denoted here by forces that are exciting those masses by a superstiff pole. So this is the equation for the forced vibration of a double degree of freedom system, and this can be easily solved. So this would can be written in matrix form in such a way. So we have the stiffness matrix, the displacement vector, and the force vector. For doing so, we can solve the equation for a specific vector, or we can simply invert the stiffness matrix, and then the solution is thus the inverted matrix multiplied by the force vector, and then we get the final displacement related to a specific load case in every frequency. In the harmonic oscillator, we had some kind of resonance concept. So what happens to the harmonic oscillator if it's started by a certain, let's say, excitation, and then it vibrates for itself? This was called the so-called resonance. If we investigate such a thing for a double degree of freedom system, we will come to the concept of modal solutions or modes. So for doing so, we neglect the external forces and we neglect all damping terms. So the equation before would be written like this. And this generates a so-called general eigenvalue problem. So we just subdividing and rearranging the terms in such a way that all those which has no omega square are on the left-hand side, and this gives us the stiffness matrix, denoted by K. And all those terms that are mass related and therefore containing a squared omega value into it, this is the mass matrix, and this is written in such a way, and this is supposed to be 0 as there are no external forces. The non-trivial solution of this equation are just given if the determinant of this global matrix is 0. And the determinant is an equation that we can solve or write out, and we replace the omega by the factor lambda. And in that case, we get something like a characteristic equation again, but this time a characteristic equation for the lambda. And this can be solved if we're using some specific acronyms, which is, let's say, which is the frequency of the left harmonic oscillator, and the right hand, the second harmonic oscillator, and a term that would correspond to the resonance of the two masses only connected by the center spring, which is called omega c, then we can write the two single frequencies in this solution of this quadratic equation on top of that. You don't have to go too much into the detail of this, but just for you to mention, we can solve this, and this can be done in a quite complex but still analytical way. So how do we get the modal solution? So it means what is the shape of this? I mean, for getting the shape, we just entering the frequency solutions here into our equation of motion in matrix form again, and we solve for this mode shapes, which are denoted by a large psi and have the index I for the two different modes that we will find. If you do so, and after some really painful math, but leading to a quite simple solution, we get those mode shapes with a frequency, a stiffness term, and some mentioned, and one here on the second displacement. For giving you a kind of brief introduction, we simplify the case a little bit. We just assume that both springs have the same spring stiffness Ks and both masses are the same. This really simplifies our problem a little bit, because that means, and if we do so, we would get for the two harmonic or eigenfrequencies, we would get two solutions. One is the simple harmonic oscillator frequency of the first, or for both harmonic oscillator, and the other one is the frequency which is slightly extended by the frequency of the inner resonance. So just which would be the case if you're just using the masses plus the spring in the middle. And let's have a look at the harmonic solutions of this. The first one, that's the harmonic frequency of the single oscillator. And this really makes sense, because the shape would be a global movement completely synchronous of both masses. So this is why the modal vector is 1, 1. If those masses are moving totally synchronously, there's no displacement or elongation of the center spring. So it is just as if two oscillators are completely independent, working as a typical harmonic single oscillator. So the situation is different for the second frequency. Here we have another resolution. We have just the opposite effect. We have minus 1, so they are just moving into exactly towards the different direction. This has the effect that we have our typical harmonic oscillator resonance for this system here, which would be omega 0, sorry for my German. But in addition, we got the stiffness of the inner spring, and this increases the frequency. So this is why we have another additional frequency here. So what is the outcome of this? So we see that even if we have more complex systems or multiple systems, we still have something like a resonance. And to this resonance, a specific natural shape of motion corresponds. And this is the mode. And that means, and this, as we will later see, is a very important concept for simplifying our multiple degree of freedom systems later on. Good. So far for 2 degree of freedom system, and now we will extend this concept to multiple degrees of freedom. We will keep still everything rectangular, but in general it shows, or it should show us the principle of a deterministic mechanical system, how this could be described and how it could be solved. So let's again consider some specific setup of lumped elements, here the springs and the masses. We will not consider any damping elements now here in addition. The degrees of freedom are, the convention is as follows. We have U and V for the X and Y direction of the displacement, and the index gives us the node number. So every mass is at a different position. So the equation of motion is written in such a way. We have the mass matrix, we have the damping matrix, which we will not use here, but just for presentation, and we have a stiffness matrix that simplifies and relates the stiffness, and we have an external force excitation that could excite any force here in this system. Again, we use the complex notation and write this in frequency domain, and then we get again our omega terms with different factors, and we get also the C factor. And just to mention, there might be some damping which is related to directly related to the displacement, as we have seen in our damping chapter, and this would be used in such a way. But anyhow, globally in the next studies we will more or less neglect our damping parts and just stay with the remaining mass and stiffness matrix. So why are we using Q? The reason for that is that we call them generic displacements. In the most simple case, this is just the direction displacement in X, Y, and Z direction called U, V, and W. But it could also be rotations, whatever, or it could also be a motion in some intermediate direction, whatever. So this is why we using, or this is common standard to use Q as a symbol for that. The same is then true for the forces. So the forces are also general forces, and they are always related to the generic displacement. That means if there would be a rotation, it would be a moment. But here we stay with linear forces and displacement in the Cartesian coordinate system. Okay, so how do we assemble those matrices in the common setup? And we start with a mass matrix, which is quite simple. So due to Newton's law, all masses have a specific acceleration, or the second time derivative of the displacement, which is given by an external force. And that means if we have an external force in several directions at several nodes, so here again, the first index is the position, the J is the index for the direction. We have to set up this equation for every point mass and for every direction node. For instance, if we do this for one mass, and we just talk about X and Y direction, or U and V for the displacement notation, the mass matrix would look like this. So one mass that could be forced in X and Y direction, and we will have those two mass entries in the mass matrix just on the diagonal. If we do this, for instance, on the system that we have seen here with 4 masses, it would exactly look like this. So just note that we always have a doubling because it's always X, Y, X, Y, X, Y, or U, V, U, V for all the 2 degrees of freedom. If we would have an additional Z direction, there would be a third entry for every mass point here. So again, this mass matrix is quite simple for this lumped element case. And it's always a diagonal. If we have a global deterministic system from an FE system, one thing is clear, it might not be a diagonal matrix, but it will always be a banded matrix. So all the off diagonal, there will not be so many non-zeros except near the diagonal. So let's come to the stiffness matrix. So now the situation is slightly different. Things are coupled now. If you just look at the spring element as denoted here, we have our spring stiffness Ks. We have the displacement 1 and 2 on the left and right hand side of the spring. And once we have external forces that would change the elongation of the spring and lead to an extra force due to the typical equation of force equilibrium. And the same is true for the other side. So that means the equation of motion for a simple spring without any mass, with external forces if Fx1 and 2 and displacement u1 and u2, would exactly look like this. We have sometimes a special situation. So if a spring is connected, not free, cannot move freely, it's just connected to a boundary, that would mean that just we take this boundary as give it a 0 nodal number, that only this part can move. So then we have again the situation as for the harmonic oscillator. So we'll have this forces which could be there. Then we have our stiffness matrix, but the U0 is definitely 0 because the wall is fixed. If we solve it, we get this equation of motion for our normal situation, but we will have, let's say that means that the force that is occurring here is exactly the opposite of this force here on the other side. But that's clear. This is a so-called blocked force that guarantees that U0 remains 0, that there is no movement at all. That is a blocked force that always is occurring at stiff boundaries. Good. Coming back to the system that you've seen before with all the springs here, we have this spring 1, spring 2, and so on and so on. And how do we set up the stiffness matrix of all those springs? Yeah, we are following more or less the same concept than before. I just give you some examples for the single springs. For instance, this is the first one here. That's the one that's connected to the wall. The only degree of freedom that is affected by this one here. So that means we are just putting this here. But that means from this matrix that we are using, it is somehow oriented here. And all those fixed degrees of freedom are deleted. So we are just using the lower right point of this stiffness matrix. If we come, for instance, to the second spring, you know, this is just moving in x direction, and that means here those degrees of freedom, this is the, we go back to our figure again, so this is just moving in one direction. This would be the u2, also the motion in x direction at the second mass, and this is the reason why we have to, let's say we distribute this stiffness matrix to the relevant degrees of freedom, which are in this column, rows, but also in this column. So the degrees of freedom that are used finally in our global vector, they denote where the location of where the entries in the global stiffness matrix are. The same happens, for instance, for the fourth stiffness matrix, which is related to the fourth one, between mass 1 and mass 2, but only in v, as in the y direction. So this is why the entries are a different location at the stiffness matrix. This time they are just here for node 1 in y direction, and for node 3 also in y direction. And the same is true for the rows. So hopefully you understand the concept. So the element matrices are distributed to the global system in the global stiffness matrix. And this is exactly how a finite element program works. So all the nodes that you will find in the global mesh of the finite element program, they calculate the mass matrices and they calculate the stiffnesses matrices using specific algorithm, which could be super complicated. Again, this is not a lecture about finite element methods, but it's very important to understand the global concept of mass and stiffness matrices in a dynamic system. And this is the concept here. Good. How can we calculate a power input into such a system? Again, we come back to our harmonic oscillator, and there the introduced power was given by the complex velocity times the force and the real part of it. This is now again a vector. So this is the velocity vector, and use the Hermitian vector of it times the force. If we would like to use the displacement, we have to use the j omega factor, but that means that we are no longer using the v part. Then we have to use the imaginary part of the displacement, and there will be an omega factor outfactored together with the half factor. And just remember, this is this is a column vector, and this is with the Hermitian context, this is a row vector. And that means that every component of those vectors are just multiplied and summed up. So this is just another way to write this equation. But anyhow, it would be the introduced power into a complex dynamic system with multiple or very complex multiple forces and multiple degrees of freedom for displacement. So Anyhow, that means the input power can be reconstructed by the dynamic stiffness matrix. Why is that? Because we can switch from force to stiffness wherever we want, because this is where we have the dynamic stiffness matrix. Or the other direction is also possible, that we generate the displacement as a reaction on the external forces. And if we do so, we can write the upper input power in a different way. If we would just rely on the displacements, it would look like this. So here we have replaced this forced by this expression, which is this one. And the other option is to go back to the displacement version. Here in this case, we have replaced the complex value by this expression here. By this expression. And then we are just using the introduced power where we know the forces and the stiffness matrix. And here we get the input power where we know the stiffness matrix and the given displacement at the boundary. Good. So if we do the same in matrix notation, it would look like this. Again, using the Hermitian stuff. Just keep in mind that this would be a vector. This would be the result of this here. Would be a row vector. A column vector, and this would be a row vector looking like this, with all entries here and all entries here, and this would be multiplied by this and summed up. So this is why this vector convention is quite helpful. Why are we doing this? I mean, this is very important. We will later need all this for the power introduced into an SEA subsystem. And this is the formula. This is exactly describing this power. So please keep this in mind. We will use this very, very often. Just one remark on notation here. The second form where we are writing this in the for the forces and using the stiffness matrix for the power input, we are using a notation like minus Hermitian. This is the complex conjugate of the conjugate complex of an inverse matrix. So please keep this in mind. This is how we are writing this. We will use this also very often in later sessions. Good. We have shown the modal concept on the double degree of freedom system, and the same is also true for multiple degree of freedom system, obviously. And we do more or less step by step the same thing than before. This is our equation of motion, and we say now we're looking for modes, creating our characteristic equation again and setting the forces to 0. Again, the 0 determinant gives us the modal frequency. We will not go through a detailed plane because this is now for multiple degrees of freedom. That's the job for numerics, to calculate the modal frequencies. And if we enter those modal frequencies, we would get the mode shapes that are belonging to the single frequencies. And it's very important to understand what are the properties of the single mode shapes. And one important property is that they are orthogonal. So that means, what that means we now see in detail. So we just assume that we have two different modal solutions, which could be m, n, whatever. So that would mean that this would be the mode shape belonging to this modal frequency. And the same would be true on the other side for another mode shape at m. And if we multiply the first one with the mth mode, and the second one multiply with the nth mode, so the other one, and then we we would get exactly this expression here. So this is just moved to that position, and this is moved to this position. Good. So in the next step, we take the difference between those two modes, and this would lead to this equation. What does it say to us? Normally, we cannot know, in most cases, or we have to assume that the modal frequencies are not the same. But this requires that this is true, that this equation here must be 0 for all indices that are not the same. And this is the orthogonality property. A very important thing is this is not orthogonal on its own. You need the mass matrix in the middle. This is very often, especially forgotten for experimental guys. The mode shape of the dynamic mechanical system is only orthonormal in the context when you use the mass matrix that's related with it. The same can also be do for the stiffness equation. If we do so, we get it's also orthogonal for the stiffness relationship. So this is something that's true for both of it. For practical reasons, so now we know they are orthogonal with respect to K and to M matrices. And now it's a good thing to normalize it. And the easiest thing is now we for the normalization we multiply the second equation that's in 27. Let's go back to show it to you. So this one, we're using this one now again, and we multiply it again with Vm, and then we will get this equation here, and this helps us. So the question is now, what would be a reasonable normalization for it? And the simple thing is, if we modify, if we give such, let's say, expression some names, then we would define this expression here as the modal mass. So this is the result of the mode shape multiplied by no, this is not the modal mass, this would be the modal stiffness. And this part here, this is the modal mass. So just using the mode shapes and the matrices in the middle, and then we get expressions which are denoted by modal mass and modal spring, because you can consider this as a kind of transformation, and this gives us exactly this. So the good thing is that if we're using this expression, we get a very simple equation, and if we solve this with this knowledge, we see that the modal mass and modal stiffness is directly related to the modal frequency, which is given by this. So that's the modal stiffness divided by the modal matrix gives us the squared modal frequency. Good. With this knowledge, we normalize our modes, and we use the modal mass in a kind of in large matrix. And the simple thing is that we're just using the derived mode shape and divide it by the square root of the modal mass. And then we use another acronym, which is a large phi, which denotes mass normalized mode shapes. Why are we doing this? You will see now later. First of all, we put them in a row. We put all those modal matrices in the large vectors in the large created matrix out of it. It's not rectangular. It doesn't have to be, because it depends on how many modes we have. And and then we normalize, and if we use the normalization here on top, because of this square root of it, that means that the mass matrix with this normalization becomes unity. So it's just a row of ones. And this can be used as a kind of, it can be considered as a kind of matrix transformation. So the transposed matrix and the normal matrix from left and right of the mass matrix gives us the transformed mass matrix. The modal base in the following is always denoted by this prime here. If we see this, and it's not a derivative, it's a modal base. If we are using the same thing on the stiffness matrix, and again we denote the modal stiffness base by the prime here, we get also a very simple thing. Please remember, it was orthogonal, so only when we have the same index we get a value. And now we have the mass normalization. So here we had K divided by M, and this is, as we have shown before, this is the modal frequency. So our stiffness matrix on top looks super simple. So completely diagonal, no coupling between the modes and the resonances, and that's very practical. And you will see later why. So as mentioned, the prime denotes the coordinates of the matrices in the modal coordinates. And due to this property of orthogonality, every solution Q that we have can now be expressed in this modal base. So the real shape of displacement is a modal coordinate multiplied by the single mode, and this is just summed up. Or again, in matrix notation, we're using this matrix here, and we use the modal coordinates as a vector. The vector looks exactly like this. It's a column vector of all the coordinates, and as mentioned before, the modal transformation matrix is the list of all column vector of the single modes. If we enter this into our global equation of motion, and using all the transformation, the equation would, and then using the left and right multiplication of this mode, it would look like this. So we enter, first of all, we enter this here, this expression into our equation of motion, and then we multiply from the right hand side by the transformation matrix, or the transpose of the modal transformation matrix, and then our, let's say, our equation of motion would look like this. So this is the result that we get from entering this for Q, and this is from the right multiplication, we go at that this. But if you look at all the detailed components here, so this is the modal stiffness matrix, this is the modal mass matrix, which is unity. We can write this in a simplified way like this. And also we have now the force vector, where we have not done anything to it. We just have multiplied the force vector from the left by this transposed modal transformation matrix. And this gives us the modal force matrix, again denoted by a prime. And the good thing is, we can write this equation now down, and it looks really, really super simple. Why is that? We just have the mass matrix multiplied by omega. These are all the omegas that we have here. And the K matrix leads to all the omega 1, omega n, and on the final and last used modal frequency. So our super complicated matrix is now downsized to a diagonal matrix. And this makes the solution very, very simple. So every Qn is given by the force n, the modal force n, divided by omega n minus omega. And if you remember well, this is exactly the same equation for the harmonic oscillator. Hooray, here it comes again. So that means every complex multiple degree of system can be condensed to a set of resonators, which are the modes. That's the good concept here. Good. So far for the multiple and double degree of freedom system, and we come to the conclusions. Complex systems can be modeled by a network of discrete spring, dampers, and masses. And more or less, this is the case for every dynamic structural system. It's more complex, it's different degrees of freedom, but this is the picture that helps to understand the deterministic system. As mentioned, this is exactly what finite element programs actually do. They form the element formulation that create exactly the mass and stiffness, and sometimes also the damping matrix. A structural system can be described by natural mode shapes of vibration. And this modal base can be used to condense the dynamical problem into a simplified version. So this is something to simplify our problem, also in terms of numerics. Once you have the modes, the calculation times of all responses can be, or are definitely, much faster. Every mode can be understood as an independent oscillator. And what is also important, that's a kind of hint for practical things, if you use a problem in modal coordinates and you might see that one specific mode is the one that's causing the biggest vibration, biggest displacement, this is exactly the mode that you have to take care of. If you have a means or measure to do something for a specific resonance, you have to fight exactly these modes by vibration dampers, by stiffness, by whatever. But this is then the typical task of a vibration engineer. Good. So that's it for the session number 3. And yeah, I hope that you have enjoyed it. Thanks for your attention, and I'm looking forward to the random stuff in the next session. Okay, goodbye.